talk I gave, and people asked me about to comment about onions and what they are and how they behave, especially when we want to simulate them. So I would like to spend a little bit of time to present onions, give a little bit of general theory, and also also talk a little bit about Jones polynomials. That's a computational hard problem to evaluate them, but they are very useful. So performing a quantum simulation for evaluating them will be beneficial. So that's a problem, not a problem for you to consider. Thank you for your patience. The first slide picture on the left, the navigator mechanism is the first probably analog computer. It had a router that you rotate and it would give you the position of the 5 planets, the moon, the sun, calculated interesting things. It dates back to the 1st century before Christ. They used it for 0 practical reasons. It was meant to be as a gift from one king to another, just to impress them. Put in the office, you know, and impress your VIP guests. This is a digital computer, one of the first ones, the Robotron Z9001. And this is a quantum computer. Okay, the wave, the first one, so-called claimed quantum computer, and I'm kind of worried what will happen if you unplug this back there. But research in that direction goes very fast, and we'll see great things. One interesting thing is to change the computational class from hard problems, classically hard problems to solve, to make them easy by using quantum resources. Also, there are quantum games. So some of my favorite ones that you can do with quantum mechanics. And I'm a fan of Star Trek. Here's the starship is threatened by an external lightning. Okay, and Q comes and says, "I can help you. I can do anything." Q stands for quantum, of course. And he says, if you win a puzzle, then I'll save you. Competing Q with Picard. Okay? And the puzzle is, Q has a box with a coin that is facing heads. Then Q puts the hand inside the box. You can't see inside the box, but you put your hand. Then Picard puts his hand in. And then Q puts his hand in again. And if the coin is heads still, then Q wins and allows the thread to go on. If it turns to tails, then Picard wins and Q will save the starship. Alright? Let's see what happens. The coin, the heads or tails, you can encode in the quantum state. You have it heads to be 0, it's initially encoded. Now Q goes in, and as he's quantum, he can make a Hadamard rotation on the coin and symmetrize it, make it 0 plus 1. So whatever Picard rotated, trying to guess, you know, if Q is bluffing or double bluffing or triple bluffing, you know, but he will do one of the two. But as the state is symmetric, whatever he does, he will get back the same state. Q knows that, performs another Hadamard gate. At the end, he gets heads. Unfortunately, Picard loses. Starship is destroyed. It's just a fairy tale, right? Things we can do with quantum computers are factorize large numbers exponentially fast. Well, it hasn't been proved exactly that it's a true game, but we can do it better than what classical computers can do now. And of course, this factorizing problem, we use it, you know, you can easily multiply numbers, very hard to factorize. It's a one-way type of directional thing. We use it to encrypt information, to put passwords and so on. So if you could factorize fast, then you were a very good hacker. You can break in banks and military secrets and everything. That's why there's so much interest lately to pour money in order to get the first computer going. We want to be all hackers, right? You can search large databases with the square root, so quantum exponential speedup, but it's a very useful speedup. And you can do quantum simulations, which is the important reason, the main goal here over here. But in all these applications, errors are a problem. And the question is how to overcome them. And the example I give is really holding a cap. If the cap has no handles, then changing the shape of your fingers will result in this system not to be stable. The cap will fall down and break if it wasn't the magic cap. Okay? So a little bit of geometric change in the shape of the fingers can cause an error. Now, if you have a handle, amazing device here, and you put your finger around it, okay? Even if I change the shape of my fingers, the cap remains there at all times. I entangle myself topologically, not trivially, myself with the cap. And of course, this type of stability, we're using it all the time. And I agree, it's a very classical type of stability, but it's exactly the type of stability that we would like to build inside quantum systems. It's a classical type of stability that has quantum consequences. So here is a cap with a handle. Of course, that's my favorite cap. It has two handles, so when you hand over a cap to a friend, they don't need to burn themselves, right? A cup of tea, they go, oh, nice, how nice. Or when you walk to your office with a cup of tea, you need to open the door, you can easily change hands, pick up your keys, open, change again without burning yourself again. So that's absolute favorite. Every physicist to have one. I'm not quite sure what this cap is good for. So topology does promise to solve the problem of errors, and importantly, it is a lot of fun. You learn very nice physics, very nice mathematics. It's kind of, when I started this topic, it sucked me in, and I haven't been able to go out of it. So if you want to learn things about it, there is an interesting book. It has a very long introduction. You can read it before sleeping, 15 minutes, and you can go through the first 4 chapters easily. And then it has more advanced materials later on about the Chern-Simons theories and many topological models. You can download it on the web if you don't care about paper. It's on my webpage. The difference between geometry and topology, geometry cares about local characteristics, okay? Curvature and so on, and lengths and scales. The topology is not. It cares about a very specific small number of information about shapes, and I'll pick up nodes and links as my objects, and I'll be talking about the topology of these objects. So while these 2 links with 2 strands, they are not geometrically equivalent, the curvature up here is not the same as the curvature there, they are topologically equivalent. This has 6 crossings oriented in the same way. Here I just brought them all together. So in terms of topology, as knots are going, these two are equivalent. This was all classical, what happens in quantum mechanics. Why quantum mechanics exhibits topological effects. The first, simplest, and most important topological effect in quantum mechanics is the Aharonov effect. You have a flux phi going through a solenoid that is confined inside the solenoid exponentially, and you have a charge particle length. As you rotate it around, its wave function acquires a phase factor, which is integer multiples of a number. So this integer property is what makes it topological. Okay? If you change the shape of the path, this phase factor won't change if you keep the number of circulations the same. That's a topological property. Now let's talk a little bit about statistics and use the idea of the Aharonov effect. And now this is a very tricky topic I would like to talk to you. Okay? A little bit of attention. It won't be magic trick. I have two particles which are identical, okay? And I write a wave function about them. The question is, what happens if I change the two particles? If I close my eyes, somebody changes them, I open the eyes again. Can I notice a difference? The particle is identical, which means that the local physics should be identical. If I make a local measurement of the position of the particles being exchanged or not, I shouldn't be able to see any difference. But still, there could be some local physics that changes. I have a wave function, a common wave function that describes both particles, psi, okay? This wave function can change in a way that local measurements cannot detect. And it's exactly what statistics is about. You allow your wave function, your local properties to stay the same, but there is still enough space to change the wave function in a non-trivial way. Okay? That's a very similar property to quantum error correction, if you like. So that's why actually this requirement makes topological system to be mathematically equivalent to quantum error correction. Nowadays in the laboratories, the quantum error correcting codes are using the weapon of choice of experimentalists due to efficiency are topological models implementing or simulating topological models. Joseph Sujanis, for example. So the wave function can acquire some change, and we'll see now what that change could be. For simplicity, just to make my life easier, I will allow a double exchange, not a single one, a double one, which is equivalent to taking one particle around the other. Okay? As I said, I want just to change the position of the particles. I don't care about interactions, and the shape of the path I'm exchanging them doesn't matter. I just want to move them from one side to the other. I can do it in a physical way, but they don't interact. Okay? Zero interactions. I just want to get the statistics. So let's look at the 3 dimensions. I have the 2 particles there, identical, and I move one around the other. But this path, I can change its shape, okay, and I can deform it to a path which is inside, bypasses the particle. So continuous change of the path. The wave function after the circulation, okay, should be the same, but the continuous changes of the path. And of course, this smaller path, I can contract it to the trivial path that there is no circulation taking place. So necessarily, my wave function, the final wave function that I want to calculate, has to be equal to the initial wave function. And so I have 2 changes that gives rise to the bosons, where the wave function didn't change at all, or fermions, where I get -1 and another -1 from the other exchange. So the eventual sign wave function has to be the same. So here's the fermionic and bosonic statistics in 3 dimensions. Now, if you move to 2 dimensions, things are a little bit more tricky. Maybe this exchange here is circulation of double exchange. But I cannot continuously deform this after this one. I will have to cut it, pass it, glue it together. Okay? So in other words, I'm actually assuming that my particles are hardcore particles that cannot penetrate each other and can go through. Now this small evolution here, I can deform it to the trivial evolution now continuously that nothing has happened, but I cannot do it with the big evolution. So that doesn't mean that my particles, so that means that the evolution I can assign to this one could be arbitrary. I could get a phase factor or a whole unitary transforming my wave function. I don't have to, but I could. So in a 2-dimensional world, you could have such particles of exotic statistics called ions, or you could have bosons of Fermi. There's no need. In order to make a piece about ions that want to behave like that, we can interpret them quite faithfully as composite objects of flux, localized flux at the position of the ions, and a ring of charge going around it. Okay? And in that case, when I'm circulating one ion around the other, the charge of one goes around the flux of the other, so the Harnack-Bohm effect will give you the certain phase. So that will give you a phase factor here. And this mechanical analog is more or less what happens with the fractional quantum Hall effect. It's very faithful. If you have non-abelian, because for the Chern-Simons series I described it, a charge also creates a hole that flux passes through, the background flux. In order to have non-abelian, of course, statistics, we don't have non-abelian gauge fields, free probable charges, even more defined. But we can resort to Berry phases, or non-abelian Berry phases, where the adiabatic change in the position of the particles causes an adiabatic change in the Hamiltonian, gives rise to geometric evolutions, and you can then get what you want. And indeed, that's how you get non-abelian statistics effect. Okay, how can we construct these systems? Physically, we need ions in the fractional quantum Hall effect, topological insulators or superconductors, as we saw yesterday, all data systems that are engineered, and many others. What is it? Well, it's a 2-dimensional system of fermions or bosons or spins that interact. Okay? They interact heavily, and they create highly entangled states between them. And next, we can identify some local properties of these objects, like vortices. Okay? Some vortices quite often does a good description. And these vortices will be the anions that we're interested in. And we can forget about the little particles in the background that create the vortices. In the same way as if you create a vortex in the water by spinning it around, you really don't care about the water molecules, you care about the vortex, and you're really excited about it, right? So we're looking at the vortex, and then we can say what are the properties of the vortices. But of course, there is another system and another Hamiltonian that gives rise to all these properties. So we can create these vortices, these anions, let's say, on the 2 dimensions, and it's important if they're braided or not. So we will keep track of their position by drawing the word lines. Okay? And if the word lines are entangled, then we have an evolution, a braiding evolution of the anions, the wave function is changed or not. So possible evolutions are I can change, as we see here, this time passing. I can create them out of the vacuum. And obviously I will create a particle and an antiparticle, anion or anti-anion. Or if I have 2 of them together, I can fuse them and get another particle at the end. And we saw that fusion property for the Majorana fermions yesterday. So these are the 3 important ingredient manipulations assume I can do it. I can assume I can trap them, and indeed, as vortices are classical objects, I can really hold them, they're dressed up with quantum states, but they are classical in terms of kinematics. Okay, I can trap them and move them around and see how the wave function. So the quantum property I'm interested in is like an internal spin degree of freedom. You don't care if the speed is carried by an electron traveling or not. You care only about the spin degree of freedom, which is internal. And this analogy between the anionic Hilbert space and spin is very faithful, actually, up to the point that anions are spins with a total component of spin that is truncated to a maximum. So I have many spins, okay? I have ways how to combine them, collapsible Gordon coefficients and so on. But if you demand that I have 10 spins, but the maximum spin I can get is 1, okay, then I'm only allowed to have highly correlated states. Because I have to know that if I start combining it, I should never go above 1, spin 1, okay? And this is exactly how anions behave. It's exactly what they do. And that's the same mathematics we'll use to describe that. That's exactly also what happens in the fractional Hall effect, how you derive the Hilbert space of anions. Anyways, let's get a little bit more abstract, all right? Let's see what anions have to do with knots. So we said we can initially create them as time passes. My plane 2D plane moves down. So I create anions, I can braid them, and then I fuse them, and I ask the question, if I fuse them at the end, do I get the vacuum? That's why I haven't drawn anything here. I'm after the vacuum at this point. So I create from the vacuum, I do my braiding operation, then I fuse them at the end. What do I get? Okay. So that will be my question. And then braiding operations change the initial, the input state with this B unitary statistics caused by the statistics. And I can forget the background system. Okay, all the information of the evolution is given by these word lines, this knot. So I can simulate knots with anions, with the word lines of anions. Okay, and this is quite interesting. And I'm interested to see how the quantum state of anions changes as I'm performing, I'm simulating the knots. Okay. And let's see, and this is important because all the information of the knot should be encoded in the quantum state of the anions. The quantum state doesn't care about the exact position of the anions, it just cares if you linked once or not. Okay? So, and that's exactly what we said. If two knots are equivalent, I don't care about the shape of the string, I just want to know if they're braided together or not. So they have a promise to address exactly this problem of equivalence of knots. Now, in order to understand the equivalence of knots, there's a little bit of geometric mathematics that is very much fun. Okay? And I'll present them to you, and we'll see how Jones polynomials come about. Just a couple of slides of nice pictures. And then you have the fun of doing algebra with drawing pictures. It's really great fun. I love it. First of all, if you have two links and you want to see if they're equivalent, what type of operations, of local operations, are you allowing to do? For example, if you have a twist, you're allowed to untwist it. Okay, that won't change the knottiness of your knot. Okay? Also, if you have two strands, one is clearly behind the other, and you can easily slide one through, then you allow this operation to happen. So obviously, it won't change the topology of your knot. And apparently, you need this operation. If you have a crossing and you have another strand below, you can slide it through the strand. It's in the background. It's like some passerby in the background. Again, you can change it. And Rademeister showed that by employing these three moves, you can show that two knots are equivalent if they are continuously deformable. So these three local operations you can apply to any arbitrary number of times, and you can transform between topologically or continuously equivalent knots. Good, so we have these three operations. Now, the second bit I would like to introduce you, which is actually quite exciting, is how from a picture, because we have knots, right, things we draw, we can get into numbers. Okay, because I want to get the Jones polynomials, as polynomials with numbers, right? Can you write equations about pictures, right? Can we mathematically describe beauty, for example? Well, let's see. I'll use these two decompositions. I want to, if we have knots and links, I don't care about crossings. Crossings make my life hard, okay? So I want to undo them, and the way to undo them is to use these skin relations. If I have a crossing of this type, I undo the crossing with two parallel lines. So I go to the link, I remove this part, and I substitute with two horizontal lines or two vertical lines. And I introduce a number, a, and a 1 over a. And also if I have a crossing that is of the other type, actually it's a 90-degree rotation of this one, then you just get a 90-degree rotation of this too. So for every link within one crossing, I substitute two other links. One has horizontal lines with coefficient a, the other has vertical lines with coefficient 1 over a. And at the end, if you do it to all crossings, you'll end up with just simple loops. And for these loops that don't cross each other, for these loops, you assign a number like this, a d, that is a function of the x, a particular function of the x. And why this function you will see in a minute. So this is the skin relations. We have the Radameister moves that transform between equivalent links, and the skin relations that decompose links into numbers. Now let's see if the skin relations actually satisfy the Radameister moves. It's not exactly, I can do that because I know that this one should be equivalent to only this one. So can I apply the skin relations here to these crossings and get this link only? I don't know, let's see. Let's apply the skin relation this one. So I need this guy transform into two parallel, substitute this link to two other links by decomposing the upper crossing. And I need a parallel here, vertical here with 1 over a and a coefficient. All right. Let's do now this crossing. So this plot will give me 2 more graphs, and this graph will give me 2 more graphs. So this one is the crossing of this type, so I have a parallel. So 1 over a times a is 1 parallel here. And then 1 over a times 1 over a, 1 over a squared. Again, vertical, so I have this. So I throw everything else the same, I'm just modifying locally the crossings. And you get this 4 things. Now I have a loop here, and this loop gives me a minus a squared minus 1 over a squared. So I can remove it and substitute this number. And then you will see that actually this guy cancels this guy, and this guy cancels that guy. So you need that diagram, which is nice. Actually, that's why we choose to have that particular value, so that Radameister moves are satisfied. Okay? So the skin relations are in agreement with the Radameister moves. They decompose a link, and they keep only the topological information. If they satisfy the Radameister moves, anything you write down doesn't care about geometry, it cares about topology. Okay, that's an important issue. If it satisfies the Radameister moves, it means that 2 links that give you the same Jones polynomials should satisfy, the Jones polynomials should satisfy the continuously deformable to each other. So similarly, you can show that Radameister 2, this Radameister move 2, so 2, this Radameister move 3 is also satisfied. So you have a link, you go to every crossing, you decompose it, at the end you get a polynomial. So this polynomial you get is called the Kaufman bracket. Okay? Kaufman himself calls it the state sum, but everybody calls it the Kaufman bracket. And it's a polynomial as a function of A. Okay? A is a parameter, it's a complex number in general that we insert outside. If you give it a value, the polynomial will become a number. And you can calculate, you can pick up any figures of A, twists or links like that, or trivially. You can calculate this easily. I mean, you can sit down and do calculations of that form. In order to get from the Kaufman bracket to the Jones polynomial, you have to add phase value. Use the Kaufman bracket. I add a phase factor on the top in order to make it invariant against the twists, the Radameister move 1. So the Kaufman bracket is not invariant, it gives you a phase factor. You see here, a twist here gives you something non-trivial. So I is actually minus 3. So what I do is add a phase factor that counts the number of twists to the opposite power so they get cancelled. Now I get the Jones polynomial that is invariant against all the Radameister groups. Okay? And what can I do with it? So you can show that it's invariant. Good. I have a mathematical object, the Jones polynomial, that I derive from a knot, okay? And I can use it to see if two knots are equivalent. So I have another knot, I calculate the Jones polynomial, and another knot, I calculate the Jones polynomials. If these Jones polynomials are not equal, it means that the knots came from are not equal. Because if these were equal topologically, then the corresponding Jones polynomials should be equal as well. Okay? But of course, if the Jones polynomials are equal, it's not necessarily true that the knots are equivalent. Actually, this is a very hard mathematical problem to find something that distinguishes between all knots. Not that the Jones polynomials do not do that. And this is important to calculate that. I mean, distinguishing between knots is a very hard problem. It's been recognized through a long time as algorithms that distinguish between two different knots existed through the 60s, please.
And you said that there are other ways to absolutely that two Jones polynomials are the same as two of the knots are the same.
We have examples of different.
Does there exist a complete classification of knots using something else?
Sure, you can use the actual knots, but we want an efficient way. So there are mathematical tools that go a little bit beyond the Jones polynomials that do that, that try to do that. It hasn't been proven. But of course, you could use a matrix that describes the whole knot, but this is too much information, let's say. A polynomial is much easier, a number is much easier. So we want an efficient encoding, if you like. So there's a common problem also because you want to keep only some small part of information of your knot, not everything, not all the geometric. And this is also we have with speech recognition problem. You know, when you say yes, if you make a Fourier transformation of that, you get all the different frequencies and infinite number of information. But really, the information in the past is very simple, right? So it's a very similar type of algorithmic complexity problem. Intriguingly, the word to solve in Greek is lino, which is actually equivalent to disentangle things, like undo your laces. So it was recognized through the ancient times that to undo knots is a very complex process. And it was in Phrygia, the town of Phrygia, they didn't have a king. They had a knot, a very complex knot. And the myth goes that the person who could undo the knot will become the king of the town. You don't need to have a war, you don't need to fight, just undo the knot if you can, and you can become our king. And Alexander, while he was conquering and chopping and killing, he went there and said, okay, the knot. Okay? He thought a little bit about it. Of course, he took his sword and cut it through. He cheated. Okay? And then he became the king. Yes. But Jones polynomials can't actually distinguish between the knots. And what we can do is actually use anions to extract the Jones polynomials. We prepare the anions in some initial state by creating them in paths. We braid them by simulating the actual shape of the knot. The braiding operation is here. And then we fuse them at the end, which is the same as sandwiching with the initial state. So we bring them together and we want the vacuum to come out at the end. And as this evolution, this amplitude here, is invariant under continuous deformations of the knots. It means it has all the important information of the topological information of the knots. And it's given as a function of the Kaufman bracket. So that's what the amplitude is. Actually, you can show that this amplitude here is the Kaufman bracket of your algorithm. So it's a kind of new algorithm. And its evaluation of the Jones polynomial is a hard problem. It's as hard as a problem as it can get. And it's been shown that the approximation of the Jones polynomials by a quantum computer is efficient by anions of anionic simulation. This problem was first presented by Friedman, Vidal, Larsen, and Wang as a small paragraph in a pedagogical article. It was really fun. I didn't write anything about it, but of course people came mad and started working on it. It was Aharonov, Jones, and Landau that translated to a quantum algorithm. The Aharonov is not the Aharonov, it's the niece, which is an amazing scientist. Jones is the Jones, and Landau is not the Landau. So later, experimentalists together with Kaufman and other colleagues, they made quantum simulations of the Jones polynomials with NMR. So, but very simple ones. So it would be intriguing if with photons we can actually do something much more complex because we have the scalability of many operations is already there. So you have some anions and then you can manipulate them many, many times. So it's very intriguing things. If you're interested to learn about the complexity, algorithmic complexity of Jones polynomials, Kuchenberg. So that's more or less what I want to tell you. Let me summarize the Jones polynomials. They've been used for encryption of information. You can use them in order to design quantum money. Because it's very hard to calculate Jones polynomials, but you can verify easily the linkingness, the linking number between knots is an easily computable operation. So you can easily recognize the money, but it is very hard to counterfeit them. And also, simulating things with anions, where is the protection property, all right? The protection is that if you can keep the anions intact, their fundamental properties, you don't destroy them, then the operations, the statistics will remain intact, and the operations will be exact. Okay? So it's a fundamental property of these quasi-particles that makes the quantum gates resilient to errors. This is the interesting part. And all some ionic systems are designed now, are trying to be created in Majorana systems. So it's a huge effort to discover them and then employ them for technological advances. So thank you for your attention.
For the presentation, there were also already some questions during the presentation. There are some more things to clarify here. Despite lunch being here, still some questions